Let's look at Laplace transform of derivatives. Till now we have looked at Laplace transform of functions. So before we actually look at that, let's look at a definition. A continuous function f of t for t greater than 0 is said to be exponential order if the following limit holds. That is, limit as t approaches infinity of e to the power of minus st f of t is equal to 0. You know what this basically means is that even if the f of t doesn't go towards 0 as t goes to infinity, the moment we multiply it with this, if it goes to 0, then we say that this is a function of exponential. Let's look at Laplace transform of derivatives through theorems. So theorem 1, let f of t be of exponential order and have f prime of t, which is the first derivative, which is continuous. Okay, so f of t has a derivative and that derivative is also continuous. So if the Laplace transform of f of t is equal to f capital F of s, then the Laplace transform of f prime of t is equal to s capital F of s minus f of 0. This theorem says that the Laplace transform of the derivative of f can be evaluated through this simple algebraic expression. Let's prove this. So Laplace transform of f prime of t is equal to the integral of 0 to infinity of e to the power of minus st f prime of t. This is nothing great. Yes. Now let's integrate by parts. So e to the power of minus st f of t, difference integral of f prime of 0 to infinity minus s 0 to infinity integral of 0 to infinity of e to the power of minus st f of t dt. Yes, let's evaluate this. If we put infinity above e to the power of minus s times infinity, we get e to the power of minus infinity. This is as good as saying 1 by e to the power of infinity. Now 1 by infinity actually gives you 0. So 0 minus, now let's substitute 0. E to the power of 0 is the same as 1, right? E to the power of 0, anything to the power of 0 is 1 times f of 0, minus into minus plus s times. Now what is this part? This part is nothing but the Laplace transform of f of t. So which means we can say f of 0 plus s times Laplace of f of t, which is equal to, let's switch their places. So s, now this can be written as capital F of s minus f of 0, which is what we had to prove. Yes, let's look at the Laplace transform of higher derivatives. So let us say we want to find the Laplace of f double prime of p. Now, this is nothing but s square f of s minus s f of 0 minus f prime of 0. Okay, so let's prove this very quickly. Laplace transform of f double prime of p is equal to, we can write this as Laplace transform of f prime of p and its prime. Yes, we can write it like this. So let's write the Laplace transform. We have already looked at the first derivative, so that can be written as s times Laplace transform of f prime of t minus f prime of 0. S times Laplace transform of f prime of t minus f prime of 0. Right, now we apply this again. So this becomes s times, again when we apply we get s of Laplace of f of t minus s times, no, f of 0, f of 0 minus f prime of 0. So which gives us, if we open up this bracket, we get s square. This can be written as f of s minus again s of f of 0 minus f prime of 0. So, if you do it third derivative, fourth derivative, you will see a pattern emerging. So, in general, we would be able to say that Laplace of the nth derivative of t is equal to s to the power of n f of s minus s to the power of minus 1 f of 0 minus s to the power of n minus 2 f of 0 f prime of 0 minus s n minus 3 f double prime of 0 and so on till we reach f to the power of n minus 1 of 0, and s actually becomes s to the power of 0, so that becomes, so using this we can find the Laplace transform of any numbered derivative. Now let's look at the next theorem. Okay, as per this, if Laplace of f of t is equal to f of s, then Laplace of t times f of t minus f prime of s. Okay, let's again prove this. By definition, f of s is equal to Laplace of f, which can be written in integral form as 0 to infinity of e to the power of minus st of f of t dt. Now, f prime of s would be equal to what? Differentiating this integral. So 0 to infinity of e to the power of minus st. Now, the order doesn't matter, differentiating and integrating. So let's take it inside. So 0 to infinity of d by ds of e to the power of minus st f of, so now let's differentiate this. So 0 to infinity of, so when we differentiate, what do we get? This e to the power of minus st is the only thing we have to differentiate. F of t doesn't contain s because we are differentiating with respect to s. So we get minus t times e to the power of minus st f of t. This minus can come out. 0 to infinity of, let's rearrange this, e to the power of minus st tft. Let's treat this as a single function. Then what happens? How does this look like? This is nothing but the Laplace transform, right? If you treat this as a single function, this whole thing is nothing but the Laplace of T f of, yes. So basically what that means is f prime of s, which is what we started off with, right, is equal to this. Now, if we just rearrange this a little bit, what we get is Laplace of T f of t is equal to minus f prime of s, which is what we had to prove. Yes. Instead of saying just t of ft, t f of t, let's take it as t square f of t, t cube f of t. So in general, what that would boil down to is Laplace transform of t to the power of n f of t is equal to, this minus will keep switching. So minus 1 to the power of n f n s. So this is what in general would be. Okay, now let's very quickly do two problems uh, to see how this actually gets applied. Okay, first one, let's say we have to find the Laplace of t cos at. Now we know the Laplace transform of cos at s by s square plus a square. Okay, so let's now if we want to do it for t cos at, then applying the theorem d by ds of Laplace of cos at. So which means d by ds of s by s square plus a square. And now let's differentiate. Minus as it is, keep it outside. Now s square denominator as it is, differentiate the numerator, minus numerator as it is, differentiate the numerator. So 2s divided by the square of the denominator. So s square plus a square the whole square. Okay. Now just keep simplifying. Minus s square plus a square minus 2s square by s square plus a square the whole square. Now if we take out this, we get minus s square plus a square. And because of this minus, if we bring it in, we get s square minus a square by s square plus a square the whole square. So that is the Laplace transform of t cos at. Now let's try to figure out the Laplace transform of t square sine at, right? So Laplace of sine at is a by s square plus, let's write it as f of s. Applying the theorem, Laplace of t square sine at is equal to minus 1 square f double prime, because it is t square, second derivative of s, f of s. This minus 1 square disappears, becomes plus. So we are left with d2 by ds square of a by s square plus a square. Okay. So now we have to differentiate it twice. So d by ds, first differentiation, gives us what? Denominator as it is, s square plus a square times 0, differentiating the numerator, minus 2as by s square plus a square the whole square. D by ds of, this is 0, so minus 2as by s square plus a square the whole square. Now differentiating this, you know, uh, involves many steps. So I have done it, so I'll just write the result. This gives you 2a times a square minus 7s square by s square plus a square to the power of 5. Okay, so that is Laplace transform of derivatives. That's it.